Welcome back. So there is another small bit of information that I need to tell you. There is something called multi-head attention. So which is learn multiple attention projections on X. Okay, so call them Z1, Z2 up to Zm. So where every Zj is a projection on instead of learning one projection, learn m number of projections. Okay, and what changes? W's, right? The projection matrices changes for each of these. Learn all of them, and define the multi-head attention on X as take all of these Z1, Z2, etc., concatenate them and multiply it with another matrix. That's it. So this, you can see this entire multi-head projection as one other composite projection, right, of taking data and projecting it onto some other space that will give you. So this also gives you a T cross dV vector, right. You will have to adjust the dimensionality of Wz that way, compute m different attentions and concatenate the representations of all of them and use another linear projection to take it to a T cross dV space. So that is what is called as a multi-head attention. All right. A transformer uses a multi-head attention architecture. Okay. Yeah. dV only. All of these attentions are of dimensions dV, no? What do you mean by add X to it?
So after we have this MHH, the dimension of X still does not match with the dimension of the output from all the multi-headed attention layers.
No. This is multi-headed attention. No, I mean the single head attention will give you a dV dimensional vector given a token. Compute m of them, concatenate them all. So you get a m cross dV dimensional representation corresponding to one token. Bring it back to dV dimensions by multiplying it with the matrix Wz. That's it. I mean, you see the entire thing as a dV dimensional a sequence of length t with dV dimensional vectors, getting back another sequence of a sequence of t length sequence of length d each, and get another sequence of length t with dV dimensions. That's it. Okay, you will have to adjust the dimension of Wz, right, such that all these concatenations gets you to T cross dV. That's it. Wv is also learnable. Yeah.
Can we take an individual attention head dimension as dV by n, then concatenate?
That also can be done, but this is how it is done. You concatenate and then project.
What is the practical way of doing?
This is how it is done. Okay. Okay. So this is multi-head attention. One other piece that is needed to complete. Yeah. Depends on how do you define the dimensions. This entire thing is T cross m times dV, correct? Yeah. Yeah. Now you post multiply this with W, fine, and adjust it that way, you get it. Depends on how do you concatenate also. If you concatenate the other way, you can multiply it, pre-multiply it as well. Depends on dimension. You have to ensure that the dimensions match. That's it. Yeah.
X is also split.
X is
Split into n parts.
No, 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 it's not done. It's not done that way. It is take the same x, project, I mean get multiple attentions, and then concatenate them and merge them. Okay, that is how it is done. What you said also is done at times, where suppose your data dimensionality is very large, split your data dimensionality into parts and learn attentions individually to all of them, and then merge is also done, but that is not often. This is how it is done in most of the cases. Okay. Okay, so there is one other missing piece that is needed. Go on.
What if we do just one big attention rather than doing multi-head?
Yeah, so the question is, what's the need to do multi-head attention? Why not we do single head attention? The empirical claim is that every head will learn different, every head is expected to learn different features of data. It's very similar to having multiple kernels in a CNN. In a CNN, we learn multiple kernels at each layer, isn't it? Multiple filters, very similar to that. That's it. You can learn with one filter. Empirically, it has been observed that having multi heads will lead to a better accuracy, a better performance. That's it. There's no mathematical way to answer this question, and that's why I refrain from answering this. Right? It's mostly empirical. See, I'm not a big fan of teaching architectures for this precise reason, because I don't know what to teach. I mean, other than algebra, okay, there is some regularizer that is being. See, please realize that at a philosophical level, these questions are exactly the same as asking why are we choosing this particular prior for Bayesian learning. Do you see the equivalence? Exactly the same question. We put priors because we believe that this is how the data is. That's it, and that's only a belief. Okay, so these are all Bayesian regularizers that have been put, and empirically it has been observed that this will lead to good performance. That's it. Okay, and yeah. So finally, there is one other type of regularizer that is done. Regularization that is done. See, so far, the regularizers that we have imposed are on the parameters of the hypothesis, isn't it? Which means you have a function h theta of x. So we had h theta of x was the hypothesis that we were considering, which is a function from x to y, and we were regularizing theta, right? But if you look at it, if h theta of x, okay, is a composite function, let us say that h theta of x is a composite function this way, where w1 and w2 are your theta, correct? Theta is w1, w2, correct? This is our theta. Now suppose I call this as w2 times z, okay, where z is simply sigma w1x. So I already told you, right? I mean, you can see the neural network or any composite function as repeated projections of data onto different subspaces. Okay. Now this entire h theta, okay, h is now a function of both theta, or h can be viewed as a function of theta and z as well, isn't it? So h can be viewed as a function of theta and z as well. Now if we can regularize theta, why can't we regularize z as well? What do you mean by that? So I'm saying that I restrict the way this sigma w1 of x is being computed. I mean, I have already restricted by making functional form assumptions. I can put more assumptions on z, right? So this regularizing the representations, okay, is something that can be done. It's also called activity regularizers and so on. So these are parameter regularizers. These are activity or representation regularizers. Okay. See, mathematically both of them have the same effect, because h is a function of both theta and z, If you can regularize theta by putting restrictions on theta, you can regularize z as well by restricting z. Okay. See, all the techniques that are, or rather a class of techniques that are used to regularize z are called normalization techniques. Okay. And there are several of them. Now, okay, there are several type of normalizations. One is called batch normalization, and this thing is called layer normalization, and so on. Now, what is the idea? Replace z, okay, with z minus mu z divided by sigma z. Actually, you scale this with some gamma and add this with some beta, nu and beta, where mu z is simply 1 by b zi's, and sigma z is the variance of zi. Okay. Now, what am I doing is that after I compute z for, see what is happening here in a neural network. Let us say that you take one particular layer, the output of one particular layer, that is what we are calling with z. Okay. Now, before we pass it through the next layer, we will do this operation, which is subtract it with some mean and divide it with some variance, and then pass it to the next layer. Now, the question is how do I compute this mean and variance is what differentiates batch normalization and layer normalization. So, first understand this normalization idea. So, what am I doing is that in a neural network, so let us say that I have a neural network this way, and this is my x, this is my first layer z1, z2, z3, correct. Okay. Now, if I am regularizing z1, then before I pass my z1 to z2, I do this normalization operation, which is a fixed operation. You see, this operation is a fixed operation. There is nothing, when during back propagation there is nothing to learn here, correct. Is that so? Actually not. This nu and beta are learned. I will come to that in a while. For now, just remember this, just look at this, let's ignore this for a while. There is nothing to be learned. What you do is that you remove the mean and scale it with the variance. Why is this done? Do you see this as a regularizer first of all? Why is this a regularizer? Because I am restricting what values that this z1 can take, right, after it goes. I am subtracting the mean and scaling with the variance. Why is this done? It is done to ensure that all the distribution of this z1 before it goes to the next layer has 0 mean and unit variance. Typically, this problem of changing mean and variances across layer is referred to as covariate shift, and to avoid that there is no covariate shift, okay, or to avoid covariate shift, you do this z scoring or normalization. That is the idea. Okay. Now, you also see a nu and beta term here, right. These are learnt. Now, why are these put? Because suppose this neural network does not want normalization, then there should be a facility to unlearn whatever you have learned here. That is why there are see you can fix nu and beta in such a way that this entire effect will be undone, correct. This should be 1 by, this should be sigma and this should be mu, that is it. So, that is why you learn this. Now, typically this is put as a intermediate layer. So, this you put a normalization layer here. See, what is a normalization layer? You just do these operations, and when you back propagate you have to take the gradient with respect to nu and beta as well, that is it. Do you understand this? Okay. Now, the question is this mu and sigma, how do we compute? I mean, what is the mean taken over? In batch normalization, you compute the mean over all the data points that come in a batch while you are doing gradient descent. Is that okay? In layer normalization, okay, the mean and variance are taken across the dimensions of data in that particular layer, not across different data points. Do you understand the difference? The difference between the batch normalization and layer normalization is that in batch normalization you compute the mean and variance by considering the data points, by considering different data points across a batch. In layer normalization, the mean and variance are computed across different dimensions of data for a single data point, and then the means and variances are subtracted for each of the dimensions. That is it. That is layer normalization.
But aren't we losing out on a lot of information?
That is why you have nu and beta. Is this clear? This is called activity regularization, right? I mean, where you are restricting the values that your z can take by normalizing it.
So is it like the models will learn when to use the normalized data or will not use normalized?
Through nu and beta, yes, they have to learn it.
Does this also help in vanishing or
Why should it help?
since we are
There is no, it does not, no, unless you have an identity, it does not help in that way. You need that identity matrix, right? We saw that the vanishing gradient problem can be solved only by having that identity connection, right? That only that should happen. I mean, yeah, that also is there in transformer, which we will write in a while, but this is not for that problem. This is to avoid that covariate shift problem, right, where you want the distribution of all the intermediate representations to have 0 mean and unit variance. And by the way, I said that these z's, right, they are called embeddings, right? They are called embeddings. Representations are also called features. Different people use different terminologies for it. Is that all right? Now we have all ingredients to write a transformer. Yeah.
So in transformers we generally use layer norm, and whereas in CNNs we use batch norm. So like how do we choose between the two?
I refrain answering that question. So empirical. There is no mathematical answer to that question. Of course, the observation is in some architectures batch normalization layers are used, in some architectures layer normalization is used. Now, how do we know what to choose when?
Sir, when we do training on complete data, let's say for all batches, will mu and
The beta, yeah.
beta be same for all normalization layers?
No, see, nu and beta are learnable. This mu and sigma will be same for all normalization layers, correct. If you do batch norm.
So let's say
Typically, right, this batch norm is only effective only if you do SGD, batch training, not the full data training.
so at the end of the training we assume that it will be equal to standard deviation and
No, the question that is to be asked is, right, how do you compute this mu and sigma during inference? During training you can compute it over batch. How do you do it during inference? Typically during inference what is done is you take a random batch of data, compute that and then use that for inference. That is how it is done. Random batch of training data, you do a random sampling from the training data, compute the mu and sigma and then use it during inference. That is how it is done during inference. During training anyway you have a batch upon which you are training, isn't it? Okay, right. So finally we will write this transformer architecture with all this, putting all these Lego blocks together. So you start with x. We have x. You have a multi-head attention here. Okay. Then we have a residual plus normalization block. See, what is a residual layer? I have already told you, right, that skip connection, that identity learning is what is called as the residual layer. So you have a residual connection and a normalization on top of it. okay, and then you have a fully connected layer. So, to get the residual you need this skip connection also, right. So, this is it is done this way, and then finally you have a linear plus softmax. And this fully connected layer, right, you have a different fully connected layer for every token of data. For multi-head attention you do it for all tokens, right, together, because you need to compute the attention. Then you have t number of dv vectors. On each of these dv vectors you put a fully connected layer on top of it individually. Okay. So, then you have a linear and softmax. Why do you need a softmax at the output? Because you are doing a classification on k tokens at the output, right. So, this is one transformer block. See, you have several layers of these in an LLM, and that is what makes it billions of parameters. This is the workhorse of the modern LLM architectures actually, right. It's mostly a transformer. Now, two questions, right. How do you backpropagate? I mean, it's pretty simple because we know how to backpropagate through an MLP, right. And also these residual and normalization terms and multi-head attention, all of them are, except for that softmax, all of them are linear operations. We know how to take derivatives with respect to them. So, we backpropagate using the ERM, that is it. Okay. You can solve all problems using this transformer, in the sense that you want to solve a classification problem. I told you, right. Okay. So, one last piece I will tell you. You can solve even the image or computer vision problems using a transformer. How? There is something called a vision transformer, okay, where, see, you need a sequence to look at a transformer, right. What is done is, given an image, you divide this image into non-overlapping patches, okay, and treat every patch as a d-dimensional token in a sequence. Okay. The paper that introduced this vision transformer, the title is an image is worth 16 by 16 words or something, right. So, basically you represent an image as a 16 by 16 cross 16 dimensional token, right, and use the same transformer architecture instead of a CNN to solve image. Remember, I told you in the last class, right, every data topology can be used with every other architecture, just that you need to represent that data using this particular form that this architecture demands. So, VIT is the state of the art for image tasks now, not CNNs. Okay. So, I mean, think about it, right. What is it doing? It is trying to capture the interaction between several patches in an image. See, I keep telling you, this is a universal function approximator, right. You can approximate any function and you have ERM with you. This is a function approximator, there is gradient descent, okay. Everything else is an art, okay. Entire Bayesian learning is an art. So, you choose what prior you want to put. In fact, there have been studies where people have shown that performance comparable to the modern day LLMs using transformers can be achieved using an MLP. That is what math says, no, right? You just have to do it. I mean, that's an art. So, what architecture to use, what should be the hyperparameter choices, how many layers should I use, can't I take this architecture this way? There is no clear mathematical answer to those questions. Everything is empirical, okay. There is just several architectures, several ways to get to the same end, several means to go to the same end. Yeah. So, today transformers are the ones that are used, because see, there are engineering hacks here, right. I mean, you got rid of the recurrence problem, which led to the long context. Now, these can handle long context, but there are other problems in that come with it, that the computation here is quadratic. Now then people said, oh okay fine, we solved the long context problem, now how do we solve the quadratic problem, and then people started asking, flash attention and linear attention and so on. That is the next frontier. There are also these, in fact after transformers came, other class of architectures came which are called state space models. Have you heard of these architectures called Mamba and so on, right? Okay fine. So these are called state space models. I will not be talking about SSMs in this course, maybe I will talk about them in the next course. So SSMs are again recurrence coming back. State space models, LSTMs and RNNs are recurrent models, they are actually state space models. So people showed that the quadratic problem in transformers can be solved using recurrence again. But what do you do with what do you do for the vanishing gradient problem? They had other ways to do it. That is it. So it's a sort of cycle, right? I mean, you come up with a new architecture, show that empirically it works, solves multiple tasks. All you need to do mathematically is show that this architecture is a universal function approximator, which can be done because there is a fully connected layer here. If you take out the fully connected layer here, this is only a linear function, and linear functions cannot approximate nonlinear decision boundaries, we know that. Okay. In fact, if there is a take home message from this particular course, this is what it is going to be. Do not get fixated on architectures, because they are all Bayesian regularizers. Okay. So focus more on the problem that you are solving, and whatever architectures, as long as it is a universal approximator and solves your problem, it is fine. So some problems CNNs do, and in most of the cases, right, I mean, but for the engineering gains that a particular architecture gives you, if it is a universal approximator, theoretically you can solve any problem using that is the idea. Okay. So we are done with transformers. So the next class I will be, maybe half of the class I will spend on how to use some of these architectures for some of the usually occurring problems. There is this thing called transfer learning, multi-class learning, and other kinds of training paradigms. We will talk about that. Okay. And from the class after that we will go to decision trees. Okay. That is what the plan is. Thank you then.